Hey, welcome back, Strengths Kids. We are going to continue using the same examples we did to find internal forces. Then we went through these examples and we wrote equations for shear and moment diagrams and drew them. And so now we have a working shear and moment diagram. We need to remember when we have negative shear, that means a negative slope on our moment line. When we have positive shear, that just means positive slope. And I know that if this is a constant, it's a 0 degree, so I end up with a 1 degree and then a 2 degree. Here, there's nothing, 0 degree, 1 degree, okay? So here's our shear and moment diagrams, and we're going to look at a couple of different cross sections and see how our cross sections kind of look when we apply that the bending moment. So we need to remember we are now back to a normal stress, but this time we are looking at normal stress due to a beam and bending. Okay, and then our maximum is MC over I. So Y is just a distance from the centroid up to a part. So it could be halfway up, it could be third up, it could be down, it could be down here. It doesn't really matter. But once I get to this very outermost fiber, and it doesn't matter where I am across this cross section, okay? All these fibers are going to be C to the top or C to the bottom. It doesn't matter where I am along this cut when I'm looking at that cross section. All of these are acting through the centroid, okay? So this is my centroid. It's going to be my neutral axis if I'm just looking at bending right now. And I can see by my formula, if y equals 0, that means I'm at the centroid. I don't have any normal stress, okay? And as I increase y from 0 to the top or to the bottom fiber, I'm going to be increasing my stress linearly. So again, you need to kind of understand why the equation looks the way that it does. So if this is my cross section, base times height, I can go over here and look, and I can see I have a negative moment. This is where you need to remember behavior. A negative moment means the curvature of my beam looks like a rainbow or unhappy. Okay, if I were to have positive moment, which we don't on this page, I need to remember positive moment gives curvature of the beam that looks like a smiley face. So if I looked at this beam, I am connected at A and I'm connected at B, and I'm loading this like a bunch of us standing on the end of a diving board. So this is going to want to go down, okay? And as it's going down, I can see that it's going to want to, if it were just a teeter-totter, it would look like this. But it's not a teeter-totter because we're connected at B. So it's going to want to kind of do something like that, okay? And I can see that curvature is indeed like an unhappy face or a rainbow. So negative moment, we can see the behavior, it's very exaggerated, is negative. When I'm negative, I have to remember I have tension top, compression bottom. And when I'm positive, I have to remember I have compression top, tension bottom. Okay, and for a square like this, it won't really matter. They'll be the same. Because for a square or a rectangle, that centroid is going to be right in the middle. That's where I can balance it on my finger. So I know that C to the top and C to the bottom are both H over 2. Okay? So as I am trying to then show the linear distribution, and we know it's linear because the moment's not going to change at this point. If I'm looking at this point and I see a negative 40, it doesn't matter where I am on the cross section. I'm cutting the piece right here and kind of looking at that cross section. It's going to be a 40. I can't just call it a negative 40 because I'm going to have positive stress where I'm in tension, negative stress where I'm in compression. So that's not going to change. Moment of inertia for my cross section will not change. What changes is that distance. So if you'll keep in mind, this looks an awful lot like shear stress due to torsion, where we had T rho over J. Okay, torque, moment. Rho is radial distance, Y is distance up or down. J is polar moment of inertia, I is moment of inertia in bending. Okay, so these stress equations all begin to look the same, and you truly need to understand the variables in each of them and how that stress then is distributed. So just looking before we do numbers, if I have negative moment, then I know I have compression on the bottom, and I'm going to draw compression on the left, and I have tension on the top. So these fibers at the top are really trying to stretch as we go around this curvature. They are having to stretch. And these fibers on the bottom, we can see they're kind of having to smush together to make that curve. So I would say we have stress. Here our stress is, Newton per meter squared, which is a Pascal. We always have to keep up with our units. And I could give you a value up here. So this is my tension region, and this is my compression region. So now let's do an example. Let's say that the height of my beam is 12 inches, and that the width of my cross section, and that the width is 6 inches, okay? The first thing I have to ask myself is, number one, where is centroid? Well, this is pretty simple. I know it's going to be right in the middle, okay? So I'm going to do something like that. I'm going to say that I have normal stress in pascals. I know where the centroid is. 2, what is I? Well, in this case, pretty easy. Moment of inertia is BH cubed over 12. We don't have to do any AB squared stuff because it's just a square. So I have 6 times 12 cubed over 12. Cross that out, and I get 6 times 12 squared. Okay? Moment. Where am I trying to find my moment? Well, normally when we design, we want to know where the maximum moment is. And usually we want the maximum positive and the maximum negative because, again, we have compression tension that have switched. And if we have a T section, we have different values of C. So that's pretty simple. So now I can say stress equals MC over I because I know the maximum is at the top and at the bottom. So let's do our stress at the top. So we are going to get 40 times 10 to the third Newton meters. That's my moment. Oh, except that I switched from inches to, I'm not paying attention here. Let's just call this kip feet. Okay, kip feet. I do apologize. I was not paying attention. So this is going to be in KSI. Okay. So I have 40 times 10 to the third pounds, but since we've switched to KSI, we're just going to call that 40 kip feet. Okay, what's wrong with this? We need to work in kips and inches. So I'm going to have to multiply by 12 inches per foot. Okay, C, that is from the centroid to the top. If this is 12 inches tall, then I know that C to the top has to be 6 inches. And then I on the bottom is 6 times 12 squared. Okay, so we pull out our handy dandy calculator, and I have 40 times 12 times 6 divided by 6 divided by 12 divided by 12, and I get a stress at the top of 3.33 KSI. And I'm going to call that positive because it truly is in tension. So I am at 3.33 KSI. If I didn't believe that it was a linear relationship, then just take, you could say sigma equals, and you could still use your 40 times 12, and we could call it 3 inches up divided by 6 times 12 squared. And I am going to end up finding that I get 1.67 KS. Oh, sorry. And you guys can't see my work, so sorry about that. I'll get better at these, I promise. So if I wanted to find C at 3 inches, 1.67, I could come back up here and graph that out, and truly that is halfway between, okay? To find where I am in my compression zone, I'm going to take the same equation, and I still have my moment of 40 kip feet. I can still multiply it by 12 to fix my units, and this time C to the bottom is 6 inches, divided by, it's the same moment of inertia, so I have 6 times 12 squared, and lo and behold, I'm going to find 3.33 KSI. Because I'm recognizing that we are in my compression zone, I'm going to call it negative, okay? Because remember, negative is compression, it's getting shorter. 3.33. So that's my positive. Okay, you can call that tension and compression, however you want to call that. So as you can see, that's pretty straightforward and pretty easy. So in this beam, if you are asked for the maximum stress, you need to recognize it has to occur where a maximum moment is. And the stress that's maximum will be the farthest away from my centroid, C. I'm going away from the centroid, okay? Now what happens if I have a T-beam? Okay, first question, number one, where is centroid? Okay, this is where you're going to have to go through and sum your forces or sum your y tilde A divided by sum of A's and get y bar. So I'm going to just make up a number here and I'm going to say that we are 4 inches to the top and we are 8 inches to the bottom and we are 2 inches up to where we meet. Okay. And number 2, I have to find my moment of inertia. And here, because I do have this compound shape, I'm going to have the sum of my moment of inertia plus AD squared. If you don't remember how to do this, I really recommend you go back and you watch the videos that are posted as a review on how to find centroids and moment of inertia. They're a statics review. They are listed in the tab, I believe, called Review. Okay, you have to know how to do this for this exam. So once I calculate a number, we're just going to make up a number. We're going to call it 100 inches to the fourth just for ease, because you should already know how to do this. And I'll work another problem straight through. I just wanted to show you the distribution. So now when I look at something like a T-beam, okay, I know that at this centroid, when I plug in stress equals my over I, that at the centroid y is 0. So my stress will be 0 here. Normal stress, KSI, tension, compression, however you want to do that. Now, if I want to know the stress at the top, which again is my tensile region, I'm going to have 40 kip feet times 12 inches per foot, okay, times y to the top this time is only 4 inches, and then we're dividing by 100, which is very, very large for this problem. 40 equals 12 times 4 times 100 divided by, and I get 19.2 KSI. Okay, 19.2. Now, when I march up to where the web and the flange are meeting, okay, it doesn't matter that one of them is wider than the other section because we are just measuring up and we are measuring down. So if I want to know at my transition, I'm going to have stress equals 40 times 12 times 2 divided by 100. And I should get half of that, which is 9.6 KSI. Like magic, 9.6. So I can draw it through here. I do need to find the stress down here at the bottom. And ask yourself, is it going to be the same as the 19.2 or is it going to be larger? What do you guys think? If it's linear, when I write my equation, stress equals my over I now have to use 8 inches because I'm going 8 inches to the bottom. 40 times 12 times 8 divided by 100, and lo and behold, I get that it's actually twice. Okay, it is 38.4. Okay, so unlike stress of P over A, where it's the same throughout, and unlike our shear due to twisting torsion, where it's just linear 0, something more like that, when we start looking at stress in a beam, we can have very different numbers when we're looking at stress at the top and stress at the bottom, which is why it's imperative if you have a max positive moment and a max negative moment and you don't have a box or a rectangle, that you actually have to check both my positive moment top and bottom and my negative moment top and bottom, especially if you have a material that has a different yield stress for compression and a different yield stress for tension, like a timber beam, Okay, it's going to have different values for yielding and tension and compression, and so you have to do a lot more checking. Okay, if this was a A36 steel T section, then I would say, yay, we are less than 36 KSI. We have not yielded.